Start the recording. We have an exam Thursday. It was just like the previous exam. This will cover chapters 13 through 17. There's 80 questions on the exam. True, false, multiple choice. There's one ranking question and 2 or 3 fill in the blank. It opens at 10:15, closes at 11:30, as we did in exam 2. Any questions about exam 3? Okay, let me play sound when someone joins. Okay. If you have any questions about the exam, go ahead and put it in chat. So the exams are each 14% of your grade. Remember, the class project is 4% of your grade, and that's due on November 12th. It's a 5-minute video. You can easily do that on Zoom. And I will show the best ones on November 17th. So after exam 3, we've got 4 lectures, then the classroom presentations, and then the final exam on November 19th. Remember, class interactions, which is you typing something in the chat, is 2% of your grade. About 2/3 of you have already been in 5 lectures, and so that counts. Their classroom, you must be in at least 5 lectures during the semester. Class project is all there. So I sent this to you multiple times. This is the last edition. Again, we do not have class Thursday. We do have an exam during class time. Any questions? Could you repeat what type of questions are on the exam? Yeah, so there will be, most of the questions are multiple choice. The second most common will be true, false. And then I think there's one ranking question, where you have 2 lists and you have to match them up. And then I think there's 3 or 4 fill in the blank questions. 80 questions in 1 hour. Well, it's 80 questions in 75 minutes, yes. And it'll be actually exactly like exam 2. In other words, it'll be a single pass through. So you can't go back, unfortunately. Other questions about the exam? I don't see exam up on Moodle yet. Yeah, that's correct. I'll put it up right after this lecture. Let me make a note of that. Yeah, my mistake. But it doesn't matter because you can't do it anyway until Thursday at 10:15. Other questions about the exam? You guys have done very, very well on the exam, so I'm not too worried about it. And I should reiterate, no excuses, unless, a comet hits the North America or something like that. There's no excuses for the exam. You just have to do it. Much math on this one. It's about the same as the previous one. You do not need a calculator for it. There's, a few questions where it's like, if you double the distance, how does the luminosity go down, or things like that. But no, there's no serious math in this one. Any other questions? Okay, today should be a fun lecture. Let's get started. Okay, share computer sound. Okay, so this is, shoot. That's really irritable. Okay, let's try this again. Okay, so there's that. Okay, here we go. So today there's only 2 topics today. One is called active galactic nuclei, and the other is called Hubble expansion. And again, we're in the Galaxies part of the course. Active galactic nuclei are a very special type of galaxies. They tended to be very common in the early times of the universe. And the textbook covers this in excruciating detail. The detail that you're going to be responsible for is just the detail that's going to be on this lecture. Really, just kind of know the general terms of the different types of active galactic nuclei and the main model for them, as opposed to, all the different subtypes. Before I do that, astronomy was in the news the last couple of days. Anybody know why? Well, I'll show you. So to answer your question, Sam, we don't know. And really the answer to that question is whether the water that we found on the moon is primordial. In other words, it was formed with the moon itself, or whether it came in on comets and asteroids and then got buried so it wouldn't be destroyed by the sun's rays. Any ice that is exposed to the sun will instantly sublimate and be gone. And so it has to be in, we did believe that, and we did find ice at the craters that are in the North and South poles, where they're in eternal darkness. What we didn't expect, and what was just found yesterday, was that there was ice in deep craters, even on the sunlit parts of the moon. Can anybody tell me why this is so incredibly important that we found water in the moon? I mean, it's not just, yeah, it's a neat scientific fact, but why is it critically important for us? Yeah, so coal is probably closer to it. The thing about water is H2O. Okay, so you got hydrogen and you got oxygen. If you split hydrogen and oxygen, you get a can of hydrogen and a can of oxygen. First of all, oxygen is useful because you can breathe it. But secondly, what happens when you combine a bunch of hydrogen with a bunch of oxygen? Anybody? Rocket fuel. That's exactly right. There's not several rockets that we use are fueled with liquid oxygen and liquid hydrogen, and that's it. And so if there's water on the moon, that's basically rocket fuel on the moon, plus oxygen that we can breathe, plus water that we can, play around with and swim in. And so water is a really, really big deal. All of a sudden it makes establishing a more permanent base on the moon a lot more possible, because then we don't have to carry, tons of water there. Also, another thing that water does is it's a great shield, because one of the problems we have on the moon is that there's a lot of radiation from the sun that can crispy critter astronauts. But if they have water shielding, I mean, water is just wonderful stuff. I'm glad I have water. Okay, let's go on to this topic of today. We're going to talk about active galactic nuclei. Active galactic, you have to apologize. I have trouble pronouncing this. I'm just going to say AGN. Sorry about that. So AGNs are the most explosive galaxies in the universe, as you can see by this image here. We say active means that things are happening now, or at least the now that we observe. Galactic, these are galaxies, and nuclei is the things that are explosive are happening at the center, at the nucleus of these galaxies. So this is about 20% of the galaxies in the universe. They're thousands of times brighter than the Milky Way galaxy, and they include these extremely bright jets that are perpendicular to the plane of the galaxy, usually spiral galaxies. And you can see these incredibly long and energetic jets. They're sometimes millions of light years long. And the light that comes from the active galactic nuclei is weird. If you remember the spectral, a black body spectrum of any object is a shape similar to this, okay? And there's reasons for that, but basically anything that's glowing at a certain temperature will emit a black body temperature. And so if you look at the spectra that's coming from these active galactic nuclei, we say it's non-thermal. In other words, it's not just something that's really hot that's emitting, because the spectra is so weird. And so we know that there's something really bizarre going on. And so Art, going back to how did they discover that the water was there? Art, what they did is they observed the moon in infrared. And we can't really detect, and in infrared, there are certain lines that water will emit that they don't emit in visible light. And so if we can detect those water lines in infrared, then we can say, hey, there's water on the moon. It's a very sensitive instrument. It requires a very big telescope. And so there's really nothing in space that could have detected these lines. And so we detected them with what's known as SOFIA. SOFIA is a project where you have a very, very large infrared telescope that's mounted inside a Boeing 747. And it flies at 40,000 feet, gets above most of the atmosphere that absorbs infrared. And that's how we observed it. Okay. And so the spectra is just really, really bizarre. They vary extremely rapidly, which means that whatever is happening with these active galactic nuclei must be really small, because anything that varies very rapidly must be small. And most of them are very distant from us. So it's clear that active galactic nuclei were very common in the early universe, back when the universe was young, and they're not so common now. And so for years and years, this was a big mystery. There's at least a dozen types of active galactic nuclei. The three that you're responsible for are called Seyferts. And again, I apologize for my pronunciation. My tongue doesn't work so well sometimes. Radio galaxies and quasars. And those are the ones you're responsible for. You're not going to be responsible a whole bunch for the details of this. I know the textbook goes into great detail. Again, what you'll be responsible for is just what's on, it's on the exam guide, which is posted under resources on WebAssign, but also what we'll be talking about today. So Seifert galaxies, they just look like normal galaxies, but the cores are thousands of times more luminous. Radio galaxies, we've observed them mostly in radio waves, and what we've observed are these incredibly long energetic jets, and we've observed them in radio waves, which means that the jets have cooled down enough that they're emitting in radio waves and not in visible light. Okay. And quasars are the most mysterious of the bunch. They're called quasi-stellar objects, and they were first discovered in the 1960s. We really had no idea what they were, and they're called quasars for quasi-stellar objects because they look like stars. And for years, we couldn't understand what was going on because their spectral lines did not match any known elements. Well, it turns out they didn't match any known elements because the redshift of these quasars was just enormous. You can see here is the original spectrum, and here's the redshifted spectrum. And because of this incredible redshift of the spectra, it took years before scientists were able to identify those as redshifted spectral lines, which means these were the most distant objects known in the universe. In fact, they still are the most distant objects known in the universe. They were thousands to millions of times brighter than they should have been comparing to normal galaxies, and they didn't appear to have a galaxy associate them. That's why they're called quasi-stellar. They just look like point objects, like stars. Well, we now have better telescopes than they did in the 60s, and we've now discovered that quasars are really just an extreme form of the Seifert galaxies. They really are galaxies, but the nucleus is so bright that it outshines the parent galaxy so much that it's very difficult to see the parent galaxy. And so now we've kind of, and also they tend to be much closer to the birth of the universe than the Seifert galaxies. So it's not like quasars are anything different than radio galaxies or Seifert galaxies. They're all part of the same thing. Quasars just tend to be a more extreme version of that. And they certainly are the brightest continuous objects in the universe. There's things that are brighter, but they only bright for a single point in time, such as colliding neutron stars or hypernovas. So and without going into spending the entire lecture on the details of AGNs, I'm going to give you the punchline now. And the punchline is, what is the unified model for these three different types of active galactic nuclei? We believe that all of them contain a multi-billion solar mass black hole at the center. And what happens is this black hole is eating very sloppily. Because this is relatively recent in the universe, it's eating stars and gas and dust that happens to be around it. And as he eats it, it forms this incredibly energetic accretion disk, and it's shining in visible light and X-rays and gamma rays, all sorts of radiation around here. What advancement to the telescope helped us see several million miles into the universe? Probably the greatest advancement was Hubble. I mean, nowhere else could we, Hubble was just revolutionary in terms of the incredible increase in resolution and the ability to stare at an object for hundreds of hours. And so Hubble was just transformative for that regard. partly because these things are so highly redshifted that a lot of these galaxies you really can't see with visible light telescopes that are on the surface of the Earth. And certainly the infrared telescopes we put in orbit have really helped. Also, more recently, we do have very, very large telescopes, 24-meter telescopes that can gather a lot of light and really look back to the beginnings of the universe. So million parsecs. Sorry, Art, I don't know what you're talking did I make a mistake on the slides? So a many billion solar mass black hole surrounded by this accretion disk. And we know this because we can measure this incredibly rapid motion. So for example, if we look at the spectral lines of different parts of this black hole around a particular galaxy, we can see that part of it is blue shifted and part of it is red shifted, telling us that there's an incredibly rapid rotation, as you would expect with an accretion disk around a 1 billion solar mass black hole. And so that makes sense. So where do the jets come from? The jets come from, as this accretion disk collapses, it produces incredibly strong magnetic fields. And these magnetic fields grab particles that are on the accretion disk and spew them out in these jets that point up and down, the north and south poles. Okay. And so the question is, why are there three types of black holes, of these active galactic nuclei? And really, it comes down to what angle you're looking at it. So if you're looking down one side of it, you get one type. If you're looking off to the side, you get a different type. And we'll talk about that in the next slide. And the radiation, one of the reasons why the radiation is non-thermal, it doesn't look like something that's really hot, is because most of the radiation is coming from particles spiraling on these incredibly strong magnetic fields that form these jets. And so what happens is when particles spiral in magnetic fields, it produces what's known as synchrotron radiation, which produces a spectra as you see over here. In other words, it's wildly non-thermal. And so the fact that the spectra of these active galactic nuclei is non-thermal pretty much proves that most of the radiation is coming from the interaction of particles with these magnetic fields. To give you an idea of how strong they are, the magnetic field on the Earth is of the order of a Gauss. When you go into an MRI machine, it might be a 50,000 Gauss machine. Here we're talking about magnetic fields of the order of 10 to the 12th, 10 to the 14th Gauss. It's strong. Okay. So these jets, they're powered by the magnetic fields that are oriented in the jets, and the magnetic fields get all twisted up, and when they combine with each other, they produce these flashes of X-rays and gamma rays. And then they spew out at very high speeds. So the orientation that we are to these active galactic nuclei is what's the same with all of these, the quasars, the radio galaxies, and the Kuiper galaxies. They all contain supermassive black holes. They all have a highly magnetic accretion disk. They all have extremely energetic jets. So that's the unified model of of AGNs. What's different between them is the orientation. So if we're looking off to the side, we're seeing Seifert galaxies. If we're looking down the throat, we're seeing the radio waves coming from the jet itself. Okay. If you look directly down the jet, then you're actually looking at quasars. Okay. So I'm not going to ask you which orientation corresponds to which type of active of AGN, but what I will ask is what's the difference between these three? And the difference is the orientation you're looking at it. Okay. And you can go for the textbook for more details on this. So let's just go, we're going to review the history of this. At the universe's beginning, gas clouds would have been contracted to form these supermassive black holes. This is one of the great unknowns of cosmology and astrophysics. We really don't know how this happened because our current simulations don't have this. We don't have these massive million and billion solar mass black holes forming, but we know they must have, because virtually all major galaxies have black holes, these supermassive black holes at the center of them. And because these active galactic nuclei were very common in the early universe, we know that these black holes must have formed very early, but we don't know how. And we believe that the black holes formed first, and it was the black holes that created the galaxy because they pulled material in that swirled around the galaxy, some of which got so close they formed this accretion disk, but most of which just formed the spiral galaxy that rotated around. Now, redshifts between 2 and 3. We'll be talking more about this redshift. Redshift of 2 or 3 means the spectral lines are shifted by a factor of 2 or a factor of 3, which is fairly extreme. That means that we're talking about the very early parts of the universe. And redshifts between 2 and 3 is kind of the very early universe. And if you remember the video from last time where you saw galaxies just slamming into each other, thousands of galaxies slamming into each other, that was the redshift between 2 and 3 era. Okay. Quasars were about 1,000 times more common than they are now. So there's a maximum growth rate for these supermassive black holes. When they reach a certain size, they just stop growing just because they can't swallow enough material. And most galaxies today probably once had quasars. So the fact is that we're the quiescent version of these active galactic nuclei. Probably not our galaxy, because the black hole at the center of our galaxy is tiny by comparison. But most other galaxies, such as the Andromeda Galaxy, were almost certainly active back in the early days. Okay, so let's do some questions. The rapid variation of the brightness of quasars implies that A, the source energy is very small, B, the energy is coming from matter and antimatter, C, the energy source is rotating rapidly, D, a chain reaction of supernova occurs, E, there are many sources of energy in the core. Okay, the correct answer is A. Anytime you see rapid variation, it means that things must be happening on a very, very small region. So for example, the light travel time across our sun is a couple of seconds. And so the sun's light output cannot really vary much faster than that because there's no time for different parts of the sun to get in sync with each other. If you have one part of the sun that's oscillating 30 times a second, another part might also oscillate at 30 times a second, but they won't be in sync with each other, and so they will tend to wash out. And so anytime you see very rapid variation, then we know things must be really small. And so the rapidness of the variation pretty much tells us the maximum size of the object. So if, for instance, neutron stars rotate hundreds to thousands of times a second, I mean, we see a pulse then 1,000 times a second, and therefore we know it can't be much bigger than Chapel Hill. Okay, and that was one very strong line of evidence that these pulsars were neutron stars. So what is the most likely source of energy for active galaxies and quasars? A, collisions, B, large clusters, C, a supermassive superluminous star, D, accretion onto supermassive black hole, E, numerous supernova from rapid star formations. Five, four, three, two, 1, 0. And D is correct. That's accretion onto supermassive black hole. Now, any of the material that actually goes into the black hole, we don't see. But the vast majority of the material stays in that accretion disk. That accretion disk heats up enormously. And then a good part of that accretion disk is grabbed by those incredibly magnetic jets and forms extremely energetic pulses of energy. And that's enough for active galactic nuclei. We're now going to come back to the Hubble's law, which is going to be a major theme that's running through this course for the next 3 lectures. And it has in the past lecture and in this lecture. Remember that the Hubble's law said the farther away you look, then the faster things are receding from us. And so let's go back to the balloon so we can see that. Okay. So balloon and, oops, sorry, I forgot to share. So here we are one of these coins. And as the universe expands, we can see other coins are moving away from us. And here, let's deflate it and inflate it again. And the farther away the coins are, the faster they're receding from us. And notice that every coin has exactly the same experience. So there's no center of the, so if you're a 2-dimensional being that's stuck on the surface of this balloon, there's no center of expansion. The entire surface is expanding all at once, and you can't say where the center of that expansion is. Okay. And that's a hard concept. We're going to be going over this concept over and over and over again. Sorry. So again, here's the balloon analogy. And here's the thing. It's not that the galaxies are expanding into the universe, into space. It's that space itself is expanding, okay? And it looks like the galaxies are receding from us, but they're not. What's happening is the space is expanding. And the cosmological redshift is a measure of this expansion. The cosmological redshift is, as opposed to a normal redshift, when I see a spacecraft that's, what if instead of expanding, the universe was deflating? Would it look like all the galaxies started to move closer and closer to each other? That's exactly right, Alex. We would see all the galaxies blue shifted, and the farther away the galaxies were from us, the faster that they would be blue shifted towards us. So everything would be collapsing. We call that the big crunch. Okay. Um, so what redshift is used to determine the Hubble constant? Abby, that's a good question. We try to use the farthest galaxies because that gives us the largest baseline so we can get the most accurate results. And we're talking about galaxies that are 10 billion light years away. Really, the only way to do that measurement is with type 1a supernova. And so this was the big breakthrough in 1999, using the measurement of type 1a supernova to calculate what that Hubble redshift, what the Hubble constant is, and in particular, has the Hubble constant been constant? And I'll give you the punchline in the next lecture. So this cosmological redshift is a measure of how much those spectral lines have been shifted. And if I see a spaceship that's just zooming past me, I'll see spectral lines shifted, redshift or blue shift, based on its velocity, its velocity relative to me. That's a redshift or a blue shift. The cosmological redshift, it looks like a redshift, but it's not, because it's not a redshift of the motion of the galaxy. It's a redshift due to the fact that the galaxy itself is expanding. Okay. And it looks exactly like a redshift, but the mechanism is actually different, and the light gets stretched. Okay. Hubble's law is a consequence of this expansion in redshift. And the cosmological redshift is measured by this thing Z, which is just the ratio of the redshifted spectral line to the source spectral line. And so when we see a high Z source, that means its redshift is very high, which means it's moving very fast, which means it's very far away, which means it's really, really young in terms of the age of the universe. And this will kind of get your head warped around it, and we're going to spend an excruciating amount of time trying to get your head unwarped around this mixture of space and time. Okay, so here is just galaxies moving away from us, and let me show you a couple of simulations. Let's go back to this. Okay, so here's a simple simulation. When there's a supernova that goes off, the supernova occurred at about 1200 AD, and then we observed it at 4000 AD. Okay, so when we look back in time, we see a supernova delayed by the distance there. Okay, so if we say that, so let's reset that, supernova occurs at 0 AD. And let's change how far away it is. Go supernova. And when do you think we should see the supernova? What year? Oh, huh. Cole, thank you so much for the reference. I'll look that up. Eschermatics. Yeah, I love Escher. They did an Escher show here at the Art Museum a couple of years ago. That was just great. Okay, so that's straightforward. Now I'm going to show you a simulation that's a little less straightforward. Okay, so here what we have is we have a galaxy that's 7 billion light years away. And I'm going to play the animation of the light leaving the galaxy and see how long it takes to reach the Earth. And so how long will it take? So put in chat your guess. How long do you think it will take for light from the galaxy to reach the Earth if the galaxy is 7 billion light years away? No. Sam, that's a good guess, but it's wrong. Anybody else? Benjamin is exactly right. It will take exactly 7 billion years to get to us. Second question. When the light reaches the Earth, how far away will the galaxy be from us? The same time as the wait at the DMV, actually, yes. That's cute, Cole. So when the light reaches the Earth, how far away will the galaxy be? So yeah, so 7 billion is a good guess. Let's see if that's true. So here is the light that's coming to the Earth, and distance in light years, there's the distance between the light beam and the Earth is this red light. The distance traveled by the light beam is here. That's the yellow line. And it took 7 billion years for the light to reach the Earth. But because the entire universe is expanding, by the time the light reaches the Earth 7 billion years later, the galaxy is now 14 billion light years away. So this is what's hard to conceptualize. The universe is 13.8 billion years old, but it's about 40 billion light years across the observable universe. So there's parts of the universe that once we could observe and now we cannot. Okay. So again, there's the light. It reaches the Earth after 7. Ooh. The distance that the light traveled is 7 billion years. And the current separation now is 23 billion years. So this means the universe expansion. So Benjamin, it looks like, let me run this again. It looks like it took 12 billion years. So even though the initial separation was 7 billion years, so I was wrong. The initial separation was 7 billion years. It actually took 12 billion years for that light to reach us. Okay. And now the current separation is 23 billion years. So does this mean the universe expands faster than the speed of light? Absolutely, it does. And Einstein's special theory of relativity say no information can travel faster than the speed of light. But there's lots of things that travel faster than the speed of light. So for example, if you have a shoreline and you've got a wave that's approaching it, and if the wave hits at an angle, the question is the point at which the wave and the shoreline intersect, you mark that with a point. And as the wave comes in, that point is going to move. And if the wave becomes shallower and shallower with the shoreline, that point is going to move faster and faster. And at some point, the intersection of the waves and the shoreline is going to move faster than the speed of the waves. And in fact, you can make it move faster than the speed of light. But no information can transmit that. And so here the universe is expanding away from us much faster than the speed of light, but we can never observe that part of the universe. We can never transmit information that can reach the parts of the universe that's expanding. And so the circle of what we call the observable universe continually gets smaller and smaller. Okay. So let's go back to the simulation.
Physicists used to think that the universe had existed forever, unchangingly, because that's what their observations of the night sky suggested. Needless to say, this view clashed with the origin or creation stories of most major religions, which hold that the universe had a beginning. So it's not surprising that it was a Catholic priest, Georges Lemaitre, who was one of the first major proponents of a new scientific viewpoint, that the universe did have a beginning. Lemaitre, of course, was also an excellent mathematician and scientist, and based this conviction not just on his religious beliefs, but upon new experimental evidence from Edwin Hubble that showed the universe was expanding. This evidence, combined with the mathematics of general relativity, allowed Lemaitre to rewind cosmic history and calculate that the farther back in time you go, the smaller the universe had to be. The natural conclusion is that everything we can currently see in the universe was at one point in time, more or less at one point in space. Lemaitre called this idea the primeval atom, but of course today we know it as the Big Bang theory. Except Big Bang is a horrible name. It would be much more accurate to call it the everywhere stretch, because one of the most common misconceptions about the Big Bang is that it implies that the entire universe was compressed into a single point, from which it then somehow expanded into the surrounding nothingness. It is true that the observable universe, that is, the part of the whole universe we can see from Earth, was indeed shrunk down to a very, very small bit of space, but that bit of space was not a single point, nor was the rest of the universe also in that same bit of space. The explanation for this is the magical power of infinity. The whole universe is really big. Current data show it's at least 20 times bigger than the observable universe, but that's just a lower bound. It might be infinite. And if you have an infinite amount of space, you can scale space down, shrink everything to minuscule proportions, and still have an infinite amount of space. Kind of like how you can zoom out as much as you want from a number line, but it'll still be an infinite number line. Essentially, space doesn't need anywhere to expand into because it can expand into itself and still have plenty of room. In fact, this is possible even if space turns out not to be infinite in size, though the reasons are complicated and have to do with the infinite differentiability of the metric of spacetime. But anyway, the event unfortunately known as the Big Bang was basically a time long ago when space was much more squeezed together, and the observable universe, which is everything we can see from Earth, was crammed into a very, very small piece of that space. Because the entire early universe was dense and hot everywhere, space-time was curved everywhere, and this curvature manifested itself as a rapid expansion of space throughout the universe. And although people call this the Big Bang, it wasn't just big, it was everywhere, and it wasn't really an explosion, it was space stretching out. It's actually quite unfortunate that the everywhere stretch isn't nearly as catchy as the Big Bang. Which brings us to the Big Bang singularity, which is an even horribler name because every single word is misleading. I mean, singularity seems to imply something that happened at a single point, which isn't at all what it's referring to. It should be called the part of the everywhere stretch where we don't know what we're talking about. Basically, our current physical models for the universe are unable to properly explain and predict what was happening at the very, very beginning when the universe was super scaled down. but rather than call it the time when we don't have a clue what was happening anywhere, for some reason we call it a singularity. This ignorance, however, does conveniently answer the question what happened before the Big Bang, because it tells us the question isn't well defined. Back when space was so incredibly compressed and everything was ridiculously hot and dense, our mathematical models of the universe break down so much that time doesn't even make sense. It's kind of like how, at the North Pole, the concept of north breaks down. I mean, what's north of the North Pole? The only thing you can say is that everywhere on Earth is south of the North Pole, or similarly, every when in the universe is after the beginning. But once time began, whenever that was, space expanded incredibly quickly all throughout the universe, for a little while. Then expansion slowed, the universe cooled, stuff happened, and after a few billion years, here we are. One thing we still don't know is why this everywhere stretching happened. That is, why did the universe start off in such a funny, compressed state, and why did it follow the seemingly arbitrary laws of physics that have governed its expansion and development ever since? For George Lemaitre, this might be where God finally comes into the picture to explain the things science can't. Except that experimental evidence doesn't actually rule out the possibility that there may indeed be a time before the beginning, a previous age of the universe that ended when space collapsed in on itself, getting quite compressed and dense and hot, but not enough to mangle up our ideas of what time is. It would have then bounced back out, stretching in a fashion similar to what we call the Big Bang, but without the we don't know what we're talking about singularity part. So physics may actually be nudging us back to the view that the universe is eternal, and didn't begin after all. In which case, Professor Lemaitre might have to rethink his interpretation of the words, "in the beginning."
So a couple of questions in chat. Barak Tarski paradox. I'm sorry, Cole, I'm not familiar. So Alex, why does the universe expand? What happened to set that act into motion? Alex, we don't know. I mean, I think the videos show that we just don't have any clue. So what we do know is from about 10 to the minus 35 second on, our laws of physics kind of jump into the fray, and we can model, given the fact that the universe came into existence, or the matter and energy came into existence at that point in an infinitely small, infinitely dense point, then we can model the evolution from that point on. Certainly the fact that the universe expanded so enormously, this is called the inflation theory, and it's not so much a theory as just an observation. That we know that the universe expanded incredibly quickly in its first 10 to the minus 28 seconds. We don't know why. Okay. And you'll notice that as this course progresses, we go from things that are absolutely certain, such as the Earth is round. Well, it's not quite round, but it's mostly round. The Earth goes around the sun. I mean, we know these for an absolute fact. If those are not true, then all bets are off and we're living in a computer simulation. But this part of the course is a lot of the things you ask. I'm just going to say, I don't know, and you don't know, and nobody knows. But at least we know what we don't know. Okay, which is good. Next short video, what expands?
Physicists tell us that the universe is expanding, but does that mean we expand with it? I mean, if so, wouldn't no one notice because everything would scale up at the same relative size and it would seem like nothing had changed? Well, the truth is, the universe isn't expanding. Space is. Of course, everything else in the universe is in space, and ignoring the influence of any other forces, when the space between things expands, those things will appear to be carried farther apart. But there are other forces in the universe, and their strengths aren't directly affected when space expands. For example, gravity and electromagnetism are able to hold atoms and solar systems together because these forces are too strong for the slow expansion of space to overcome. Think of it like this. If you and your cat are standing on a piece of ground that starts to stretch horizontally between you, the ground will pull you and your cat away from each other. But if the leash is strong enough, in particular if it's stronger than the friction force between your feet and the ground, it'll hold you and your cat together as space expands beneath you. In the real universe, it's the strength of the electromagnetic force that determines the effective sizes of particles, atoms, and molecules, so that even if the space they're in expands, the molecules don't. Electromagnetism is basically the leash that holds atoms and molecules together, and gravity is the leash that holds solar systems and galaxies together. Only over super long distances is gravity's attraction weak enough and the cumulative expansion of all that space big enough to cause galaxies and galactic clusters to actually grow more distant from one another over time. We know this because the light from distant galaxies gets redshifted as it's stretched by the expansion of the space it's traveling through. Gravity certainly still pulls distant objects towards each other, but space expands faster. Basically, the cat is off the leash. This episode of Minute Physics is supported by Audible.com.
So Matthew asked a question. Theoretically, if we mapped that point out perfectly, could we create a simulation or model the universe perfectly down to the atom using the laws of physics? So Matthew, this is a point of a lot of discussion these days. Do we live in a computer simulation? And if we do, how would we know? The size of that computer is astronomical. And there's theories saying that one way that you would know that we're in a computer simulation is that all computer programs have bugs. And so we look for bugs. We look at parts of the universe that don't make any sense. So I'm not sure how we could detect with absolute certainty whether we're in a simulation or in reality. And I'm not even sure that the distinction makes any difference. Is the force between us and the moon strong enough to keep us together? Absolutely. And in fact, the gravitational force throughout an entire galaxy is much stronger than the expansion of the universe on a cosmological scale. And really only when you're talking about millions of light years can you see that expansion. When you're talking about, just a few 100,000 light years, we have galactic clusters that are bound. The galaxies orbit each other, and they will continue to orbit each other till the cows come home. And the cows come home in about 1 trillion years. If we were in a simulation, we could still do science and learn its rules. And the only question that would change is who made the simulation. Yeah, that's correct. Okay, I'm going to skip these questions because I want to come back to these. Okay, so these questions are very difficult or thought-provoking, I'm going to say. And so I'd prefer if you guys go ahead and turn on your mics and talk among yourselves about this. We're going to start with some simple questions, but the last 2 questions in the series, if they don't blow your mind, you're not thinking. Okay. So here, which Hubble plot shows the fastest universe expansion? This should be pretty simple. And feel free to either put a comment in the chat or just talk out loud. Okay, go ahead and make a choice. Five, four, three, two, one. Okay, so the correct answer is A. The correct answer is A because if you look at this, as we're looking farther away, things are receding faster and faster from us, which means if we roll the tape back, that means that these guys will collapse very quickly, which means that the universe is expanding very quickly with this and not so quickly here, because if we look farther back in time, things are just not moving very fast. Okay. So here's the same question of which Hubble plot shows the oldest universe. Like I said, these questions are going to get more difficult as we move forward. And we're going to go through all these questions and then we're going to repeat them in a lecture, which is next Tuesday. Because this is really fundamental to understanding Hubble expansion, and especially to understand the greatest scientific discovery of the 20th century, which revolves around the Hubble expansion. And y'all got this right. Okay. Clearly see C is the oldest universe because things are expanding so slowly, which means to rewind the tape, it will take a long time for things to collapse back. Okay, so that's straightforward. Now, here's a more difficult one. Where do we receive light that was emitted closest to our time? Light that was emitted closest to our time. So Cole, your comment is very interesting. What I think of is the fact that the universe can be modeled by a small number of mathematical equations is just astounding and must tell us something profound, because there's no reason a priori why that should be so. And you're right, we are always guaranteed to run into the edge of the models because our models are just that. They're just models of the universe. They're not the universe. And if they did model the universe exactly, well, that would be interesting. Okay, so there seems to be some debate here about what's the right answer. So let me go over this in a little bit more detail. We are here. We're right at the origin. And when we're looking at distance, we're looking at really bright galaxies, and then we're looking at dimmer and dimmer galaxies, and we're measuring the speed of those galaxies as they're moving away from us. So this is like Hubble's original plot of distance, which was really for him just how bright things are. So these are dimmer, 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 and they're the ones that are, that are very close to us have a slow velocity, and the ones that are very far away from us have a very fast velocity. And so the question is, where do we receive the light that was emitted closest to our time? Let's try this again. And feel free to turn on your mic if you just want to talk. And now you're getting it. The answer is A, because that is, they're very close to us, and so the Andromeda Galaxy is 1 million light years away. The light it emits was emitted 1 million years ago. Here we might have a galaxy that's 5 billion light years away, and the light that was emitted from that is 5 billion years old. Actually, a little older based on the simulation we just ran. Okay. So where do we see light that was emitted furthest from the present time? The next three questions I want you to think deeply about, because the next three questions are really the core of our universe and what's happening to our universe, and the core of the greatest mystery that we face as a cosmos. Okay, so you're correct. Answer C, that's the farthest way, and that's the last of the easy ones. Oh no, I'm sorry, there's a couple more easy ones. So which galaxies are moving away from us with the fastest velocities? This is a tough one. I guess not so tough. So Sam, the phrase that you talked about is known as the weak anthropic principle. And I actually teach an entire course on that principle. And you're right. The laws of physics that exist might be the laws of physics that are required to create life. And there might be, an infinite number of universe with an infinite number of physical laws. And we're the only one that can support life. Okay, so you clearly got this question. Okay, and let's try the next one. Okay. I'm sorry, there's a bunch of simple ones. Try this one. Which galaxies are moving away from us with the slowest velocities? And the answer is, of course, A. And which you got correct. So now this question, which has the fastest expansion rate? So Alex, why does life exist? Why isn't the universe just a conglomeration of matter without observers? Not to be too flippant, Alex, but if the universe existed without observers, we wouldn't be here having this discussion. That's really the core of the weak anthropic principle. Kind of a selection effect. Okay, so the universe is still expanding faster, even though the rate of that expansion slows down, but it's expanding faster at C. Okay, let's skip that. And here is the one of the three hard questions. So what is going on here? A, the universe expanding rapidly and then slowly. B, the universe was expanding and then contracting. C, the universe expanding slowly and then rapidly. So what's going on here? The universe is expanding rapidly and then slowly. The universe is expanding and then contracting. And let's relaunch the poll. So Matthew, isn't this just finding the slope of the line? Yes, that's correct. So Matthew, which choice are you going to make? Okay. So here's the thing. If you look here, I'm sorry, you need to stop sharing that. Okay. So if you look here, this is the early universe. This is the universe as it existed at the very beginnings, because it's the farthest distance away from us. And there, the universe, the expansion velocity is not changing very much. Okay. So that means that the change in velocity, that the universe is expanding, but its velocity isn't decreasing very much. Whereas here, towards our time, the rate of expansion is much greater. Okay, so the universe is things are close to us. The velocity as we move from galaxy to galaxy is changing very, very rapidly. Okay, so here things were happening slowly. Here things were happening rapidly. Okay, here's another one. What's going on here? The universe is expanding rapidly and then slowly. the universe is expanding and then contracting, or the universe is expanding slowly and then rapidly. Okay. So here's the thing. Here, you can see that the velocity in the early part of the universe, the velocity is changing very quickly, okay? Here, in present day, the velocity is changing very slowly. So the universe is expanding very quickly, and then the universe is expanding very slowly, okay? Relatively speaking. And so now, this is the crux of it. Which universe do we expect to see? Given the fact that gravity is always attractive, which graph should we expect to see? Will the universe ever stop expanding? Morgan, we will talk about that in excruciating detail in lectures 22 and 23, the 2 lectures next week. And for any of you that are really interested in this subject, I deeply recommend The End of Everything by Katie Mack. She's my colleague. She's co-teaches this course in alternate semesters. Okay. And so here, the universe is expanding very quickly, and then that expansion slows down as we get closer to our time. So you would expect that something that's gravitationally bound, when I throw something up in the air, the expansion slows down as gravity is attractive, okay? And since gravity is always attractive, what we would expect is the universe would begin its expansion very quickly, and then that expansion rate would decrease over time. And so it's slow. And then the question that Morgan was asking, would that expansion ever stop and possibly reverse? We'll be answering that next time. I'm done with the lecture, so I'm open up for questions, and feel free to turn your mic on. Why wouldn't we expect it to contract just like the pen came down? So Matthew, here's the thing. When I throw this pen up, it comes down because I haven't reached escape velocity, okay? And that escape velocity depends on the mass of the Earth, and depends on how far I'm away from the Earth, and depends on how fast I throw this up. If I threw this pin up at 17,500 miles an hour, it would never come down. And so the question you're asking is, what is the escape velocity of the universe, and have we reached it? And that escape velocity of the universe depends on how massive the universe is. Now, we pretty much know the size of the universe. There's some debate about the mass of the universe. And so the universe is really supermassive. You're right. The pin will stop and then we come down, and then we have what's known as the big crunch. But if the universe is not massive enough so that the escape velocity is relatively low, this pin is just going to keep on going up and up and would never come back down. Other questions? I'm open up. You're free to turn on the mic. So Ward, yeah, we showed a video of the NASA announcement just at the beginning of class. And that's exciting. It's exciting because it means that we've got the potential for rocket fuel. We've got potential for water to drink. We've got potential for oxygen to breathe. And we have a potential of water using water as a radiation shield. I mean, water just has all these amazing properties. I think the most important is the use of rocket fuel. Will we observe other galaxies to collide in our lifetime? Sophia, absolutely. I mean, we see galaxies colliding right now. If you remember last time, we showed a video that showed a simulation versus reality, simulations of galaxies colliding, comparing that to images of galaxies colliding today. I mean, we have pictures of thousands, hundreds of thousands of colliding galaxies right now. Now, you won't actually see a time progression of that because these collisions take billions of years, but you can see galaxies colliding in every possible state of that collision, in the beginnings of the collision, in the middle of the collision, or in the latter stages of that collision. Other questions? Do not forget the exam on Thursday. I'll send out an announcement, a reminder. Any last questions on any topic at all? I'm up for anything. If the universe expansion is increasing, then does that mean everything will rip each other apart? So Blake, what you're talking about is the theory known as the Big Rip. And Katie Mack's book, The End of Everything, goes into quite a bit of detail about that. I've inherited her slides for that part of the course when she teaches that. And so we're going to go into some detail about the Big Rip. And the Big Rip is a really bad day. I mean, it's a really bad day because the entire universe is destroyed and we have no warning. And that's if, well, we'll be talking about that. Do you think there's an end to our universe, or is it ever expanding? One of the most profound philosophical statements that we've tried to understand in the 20th century is that the universe had a beginning. I mean, before the 20th century, we thought the universe was eternal, and then we discovered it doesn't. There was a beginning. And even the Christian ideas of in the beginning, before the beginning of us, there was at least a God. There was something, and we just don't know if that's true. And so in the 20th century, we said the universe had a beginning. In the 21st century, we have to come to grips with the fact that the universe might very well have an end. There is an expiration date. The question is, does that expiration date have fire or ice associated with it? We don't know, and I'll go through those different options in the next few lectures. Is there a way to determine galaxy speed relative to the Hubble flow by measuring time dilation effects between there and this galaxy? Yeah, Abby, that's a really interesting question, and I don't know if anybody's actually looked into that. Let me do some research because that's a great question. Will we see the Big Rip coming, or is it suddenly just happen? So J.J. Turner, the current theory of the Big Rip is the rip of the universe itself would propagate at the speed of light, which means that it would happen without warning, unfortunately. Well, if the universe wouldn't really stop existing, it would just get really boring. Sam, that's exactly right. That is the thought that the universe ends in ice. And that's the current leading theory for the end of everything, that we just end in ice. Things just kind of slow down and entropy takes over and there's really nothing and nowhere and nothing, nobody. But like I said, we don't know. As we talk about this layer of cosmology, it's just the amount of our ignorance is shocking. What we can say is that at least we know what we don't know, which is in the 20th century, we just didn't even know what we didn't know. So we're only a first level ignorant, not a second level ignorant. Oh, swear not by the moon? So Bree, what is that? Do we know if there's any way to distinguish the Doppler redshift from a distant galaxy from probably much greater cosmological redshift? Yeah, so Abby, that's a good question. One of the ways we do that is we assume that the universe is expanding at a uniform rate, depending only on its distance. And we can calculate the distance fairly precisely to these galaxies using type 1a supernova and other ways. And then any redshift that deviates from what the cosmological redshift should be at that distance, we say is due to local effects, the fact that it's circling other galaxies. Unfortunately, a cosmological redshift and a velocity redshift look exactly the same. And so what I described is really the only way to separate those two effects is we can measure the distance, we use the distance and subtract the cosmological redshift for that distance, and what's left over is the residuals. And then we try and make sure that everything is self-consistent, that we actually see the galaxies that this other galaxy is rotating around, and we look at all those velocity redshifts and make sure that they're all random. And you would expect that the velocity redshifts would be redshifts and blue shifts in equal measure. And if they were on one side or the other, then we know that a value for the cosmological redshift must be off a little bit. And those are calculations that people do. What's interesting is that when I was in graduate school, astronomy was looking at stars and looking at galaxies. That's really rarely true these days. For example, what I just described is extremely statistical. And so much of modern astronomy these days is statistical, measuring the statistical properties of all of those redshifts, measuring the statistical properties of the gravitational lensing, for example. Other questions? Okay, I will see you in person, well, in Zoom a week from today, and we have the exam on next Thursday, this Thursday. I think I answered that. The time dilation expected and observed. Yeah, that's correct, Abby. There's no way to distinguish it for an individual source. You do it statistically. Wow, you actually have those references. So, Abby, are you in physics? David, thank you. Wow. And you know, John Blondin's in our department. Huh. Wow. Okay. Anyway, I'll see you guys next week. It's been fun. Bye-bye.